Let's compare chlorine, bromine, and iodine. All halogens, they're in group 17, each with 7 valence electrons. They all have similar chemical reactivity. But the state of matter that they take at room temperature can be a little bit varied. Let's start with chlorine over here. Chlorine, Cl2, as a diatomic molecule, is a gas at room temperature. Now, it's kind of hard to see. The chlorine is actually above this liquid here. I'm using this liquid mixture of stuff to make the chlorine gas. But the gas itself is kind of a palish yellowish green. I've also been trying to collect it up in the syringe here, but again, it's very faint. So unless you get a very concentrated amount, which is dangerous, it's hard to see. So you might just have to kind of take my word on it. But maybe if I kind of move it like that, you can kind of see the yellowish green there. Okay, so this chlorine is a gas at room temperature. Okay, looks something like this as a diatomic molecule. Okay, our bromine, however, is a liquid at room temperature. So in this case, this darkish reddish stuff down here actually is the bromine itself, not a mixture I used to make the bromine. This is bromine sealed in a little glass tube. So let me gently set that back down there. Okay. Now you can see it's got kind of a hazy orange set of stuff above there. That is the gas form of bromine that's evaporating. So it is a liquid at room temperature, but it can't evaporate. So that tells us that it's held a little bit weakly together. Okay. And then iodine is over here. Well, we've got a solid here. Okay. Now, kind of like bromine, we can tell this is held together pretty loosely. Inside this flask here, I've got a little bit down at the bottom. You can see this kind of purple haziness inside this flask here. If I kind of tilt it around, maybe you can see a little bit better. Okay, so that hazy purple is actually the gaseous form of iodine. Okay, so it can sublimate. It goes straight from a solid to a gas. And again, that has to do with how those molecules are held together. So each molecule of iodine is similar to each molecule of chlorine, except it's got a bigger atomic radius. Each atom is a little bit bigger. Their electron clouds, therefore, are also bigger. Even though they each have 7 valence electrons, there's a lot more core electrons on the inside of the electron cloud here. So what causes these molecules to attract to each other at all, since they are, nonpolar? Okay, and if they're all nonpolar and they've all got kind of the same shape of molecule and everything, what makes the difference that makes chlorine end up as a gas at room temperature, whereas iodine is a solid and bromine's kind of in the middle? First, we should talk about the type of intermolecular force that we get in between molecules of Cl2, Br2, and I2. Okay, the diatomic versions of chlorine, bromine, and iodine. Okay, now you can call it a couple different things. You may call it dispersion forces, or London forces, or London dispersion forces. But what really tells you what's going on is the name instantaneous dipole-induced dipole forces. So what happens is we start off with a molecule like this, where this is representing a whole molecule, not just a single atom. That does not have a dipole. It's nonpolar overall. If you zoom in on this, okay, if these little red spheres are representing our electrons, they are pretty evenly distributed throughout the electron cloud of this molecule. Okay, now if I were to keep this going, our electrons are moving and kind of contained in our orbitals in a sort of probable location, but sometimes things get scrambled up and they wind up a little bit more on one side of the electron cloud than the other. Kind of like how here, my electrons are more over on the right side of the electron cloud than on the left. Okay, we'd say we have kind of a higher electron density over on the right side here. Okay, well, in this case, even though this is a nonpolar molecule, we end up with a temporary dipole. Something like this. Okay, where in the moment our molecule is polar. We have a partially negative charge over here on the right. We've got a partially positive charge over here on the left. We use this little delta Greek letter to say it's partial. It's not a full-on charge. The whole molecule is still neutral. It is still a nonpolar molecule, but temporarily it's acting polar. Okay, so again, you might call this a temporary dipole. Let me write that in here. Temporary dipole. Okay. Now, since this is a temporary dipole that happens in an instant just by chance, you could call this an instantaneous dipole also, which is where we get the first kind of part of this word, instantaneous. So in an instant, in a moment, it's like, oops, we accidentally got a polarized electron cloud. That's now a little more partially negative on one side and a little more partially positive on the other side. We got our dipole arrow up here. Okay? So what happens if this particle, this molecule, then strays over to another kind of nonpolar molecule that doesn't have a dipole? It's got a pretty even distribution of electrons, and it's just kind of hanging out like that. Well, now we've got a higher electron density, more negative charge over here on the right, okay, that is going to kind of push and repel the electron cloud over here, which means this electron cloud is going to stray a little bit farther from where it usually is, kind of over on this side. Whoops. And we end up with a little less negative charge closer to that electron cloud. So what we end up with is a very similar situation, where we now have a partially positive charge over here. We have a partially negative charge over here. And what we have made now is another temporary dipole. Right? In this case, since we caused this to become a dipole, we call this an induced dipole. So we have induced or caused and bullied this electron cloud into being polar for an instance. Okay? So this is what dispersion forces are all about. We can bring together a nonpolar molecule that just happens to be polar in an instant and cause it to go and push the electron cloud of something else and polarize it for something else. Instantaneous dipole, induced dipole, aka London dispersion forces, or some mixture of that. And this is what's happening between nonpolar molecules. We always have some little bitty attraction between them, and these can really stack up too. We have strength in numbers with dispersion forces, or instantaneous dipole, induced dipole forces. So, if chlorine, bromine, and iodine are all basically set up the same, where it's a diatomic molecule, they're halogens in the 17th column, in group 17, and they start nonpolar, what makes this difference between whether, chlorine or bromine or iodine is a solid, liquid, or gas? Why do we have chlorine, around as a gas and naturally at room temperature, and iodine is a solid and bromine's a liquid in between? Well, we could do kind of a simplified explanation, say, well, iodine is a heavier molecule. It's a bigger, bulkier molecule. So it's going to take more energy to keep it flying around as a gas rather than held together as a liquid or a solid. On the other hand, something like chlorine is lighter, so it'll be easier to keep kind of suspended and flying around and zipping as a gas rather than as keeping it together as a solid or a liquid. So you can use that. It's easier to keep a ping pong ball up in the air than it is to keep a bowling ball up in the air. But that's not super satisfactory on a chemical level. So how do we get a little deeper into this? Well, let's think of the intermolecular forces at the root of this. Okay, whether we're dealing with chlorine or bromine or iodine, the intermolecular force we're dealing with is called a London dispersion force, or just a London force, a dispersion force, or it comes down to what happens here. We start with a nonpolar molecule that happens to become an instantaneous dipole. Temporarily, it accidentally accidentally has some extra electrons over on one side of the molecule, making it partially negative on one side and partially positive over here. We got a dipole going this way, which can then influence the cloud of another molecule. Here I'm just using X's to show a generic halogen like Cl or I or Br. Okay, so we can go and affect another molecule's electron cloud by having this temporary dipole. Okay, so the electrons of this new temporary dipole can push on the electron cloud of something else that's nonpolar, which shoves away the electrons and kind of bullies them away to the other side of the molecule, leaving more of a partially positive side here and a more of a partially negative side here. So what we get is something like this. A temporary, short-lived, and weak attraction between two nonpolar molecules, one of them having an instantaneous dipole, a temporary dipole in the moment, okay, and the other having an induced dipole, which is also temporary in the moment, but caused by something else, pushing and forcing its electron cloud to be like that. We show the intermolecular force with some dots like this, okay, and we refer to this as, again, London dispersion forces, or one of those, or you can call it what it deals with, instantaneous dipole, induced dipole forces. But if all three of these have instantaneous dipole, induced dipole forces because they're all nonpolar molecules, what makes those intermolecular forces stronger for iodine than for bromine? And what makes bromine stronger than chlorine? Okay. So if chlorine, bromine, and iodine all have the same kind of intermolecular force holding them together, what makes such a difference to cause chlorine to be a gas at room temperature, bromine to be a liquid, and iodine to be a solid? Well, let's think about it. At the atomic level, chlorine is a smaller atom, and that's not about really its mass, it's more about how far out the electron cloud goes. Chlorine has a tighter electron cloud. Its electrons are bound more closely to the nucleus for a couple reasons. For one thing, it just has less electrons. So they're held more closely in. They don't have to spread out as much and repel from each other into farther out orbitals. There also aren't as many electrons kind of in between the nucleus and the valence electrons, so smaller distance means stronger kind of pull to keep the electron cloud in. It also means less shielding to repel them outwards. So effectively, the nuclear attraction to the valence electrons is relatively strong. As a result, our electrons are held pretty tightly, and so there's not much I can do to kind of pull the electron cloud out and away to polarize it. It has a low polarizability, is what we say. Now, on the other hand, something like iodine on the other extreme has a lot more electrons, so compared to what's on the outside of the electron cloud, we have a lot more electrons stacked up to repel each other, which means the farthest out electrons are more shielded from the attraction to the nucleus, so they're held more loosely. So I can more easily polarize and move around this electron cloud without it being tightly pulled in to kind of the center of each atom. So I can more easily polarize this electron cloud, which we say this is a more polarizable molecule. Therefore, we can make a bigger difference in the partially negative, partially positive of a molecule like iodine compared to the partially negative, partially positive of something like chlorine. If we have a bigger difference in the partial negative, partial positive of molecules of something like iodine, then we have a stronger intermolecular force in between them. We have a greater attraction from partial positive to partial negative, to partial positive to partial negative over and over and over again. Stronger attraction means molecules can't escape from each other as well, which means they're held together, which is why iodine is held together as a solid rather than as a liquid or a gas. Bromine has a somewhat polarizable electron cloud, not quite as polarizable as iodine, so it sticks around as a liquid, but it's stronger than chlorine's. Chlorine is pretty weakly kind of attracting to itself. Since the electrons are held so tightly to the molecule, okay, it's hard to get a difference a partial negative to partial positive, which means one molecule to another is not going to attract as well. We have a smaller intermolecular force in between each molecule. And as a result, they don't really kind of keep together as well. They can escape each other much easier and fly around as a gas, rather than kind of rolling past each other as a liquid, like in bromine, or holding tightly together and just vibrating as a solid, like iodine.